stiffness is a huge one, and of course the fabrication process. And all of these are intertwined with each other, so it's always an iterative process. But you kind of have to start somewhere, and usually you start with thinking about what is the range of motion you're gonna need. Now, just to get started real quick, I brought a couple books with me that I use a lot. This one is the best book you could possibly get for machine design. It's called Fundamentals of Machine Component Design. This is what my entire career is based on, is this book. And inside of it, you can see I don't ever do that, but I actually did that this time because there's so many things that are important in there. Basically, it takes you through every type of system. First, you go through basic statics, so that's like what kind of forces are in your structure. A little bit on dynamics, FEA, but then it gets you into material properties, and really interesting things are more than you ever wanted to know about fasteners. Screws, springs, clutches, cams, anything you wanted to know, bearings, all that stuff is in here. And so it's a really good reference, and it's really designed to teach you, like here's examples of bearings here. It's really designed to teach you exactly the stuff you need to know in order to build robust machinery. So I highly recommend it. There's a whole section on gear trains we'll talk about briefly also. And then the other one here is a book called Exact Constraint Machine Design Using Kinematic Principles. So if you see a precision, like a lot of what you see around you is not necessarily precision machinery, but if you go to something like an advanced light source at one of the national labs, all of that is super precision machinery. And they really need to figure out exactly how to line up everything so it's perfect every time. And they use these principles called exact constraint. The idea being is that for every body, it has 6 degrees of freedom. It can translate in X and Y and Z, and it can rotate around each of those axes, around X, around Y, and around Z. And so you want to be able to constrain that as much as possible. You want to know exactly how you're constraining it so that you know how each piece of the mechanism is affecting the overall position of the system. And you can take advantage of that to help you understand your range of motion. The thing that happens is if you over-constrain a device, that means you have more than one mechanism holding it in place. You don't necessarily, it becomes statically indeterminate. You actually don't know what the loading is inside each of those beams, and you can overload those beams. You're adding pre-stress to the beams, or self-stress, and that means you're taking it closer to its yield criteria before it's even taking any of the load that you're expecting it to take. And so that causes a lot of failures. It also causes a lot of issues in the assembly process, because you're trying to push 2 pieces together, but it turns out that you have 2 locating features that are fighting each other, and so you kind of have to wiggle them around, and you end up kind of mashing something into place, and so you get inconsistent assembly steps. And one of the things, a lot of people have Apple computers here. One of the things Apple's really good about is managing all of these tolerances that build up from all the different constraints that you set on the assembly process, and they manage all these so that you get these really clean packages with like nice lines. Like when you run your hand across it, like you look at your laptop and it's perfectly flat across the top face of it, right? I have this ThinkPad, and all across the bottom here, there's this bulge. That's this bulge because they try to shove a bunch of stuff in there, and they weren't really keeping track of all the tolerance stack of everything that's needing to fit inside of there. And they didn't care that they're not driving that. But if you manage all those constraints, then you can actually get really nice hardware. And that's what we're just going to talk about a little bit. So let me show you an example. There's this pretty cool set of examples here. Let's see if this link works. Let's see. First, let's start. Whoops. Can I not grab it from here? All right. And escaping is not the right button to push. And I seem to have lost my duplicate screen. Sorry, hold on a second. I don't know why that just changed. Okay.
I was offended by your bulge comment.
Yeah, guess so. I wanted to show you this link here, so I'm just going to grab it. This is, there you go. So robotics is one of these things where it really ties in. Robotics is all about machine design. It's all about the the combination of mechanical and electrical systems, and you really get into crazy mechanisms. This is something that was actually built by, I think it was GE. GE was really into some really crazy, huge robots when they're building up their nuclear power plants, and of course there's the whole issue of how do you maintain them. And so there's some really awesome graphics of what they were thinking. They actually built this thing. It's just amazing. Here's a guy climbing in and out of it. And it's just some motivation for machine design. But yeah, sure. I think there's some people swinging on it at some point. But so here you start to get into, they have some of the drawings of the internal mechanisms. And I highly recommend doing patent searches for different types of mechanisms, like differentials or gearboxes or anything like that. Because the point of the patent, or at least in the old days, the point of the patent was to describe how someone reasonably skilled in the art could actually build the thing. So you can actually see the internals of a lot of these gearboxes and transmission systems. You may have to look at it for a little while. The resolution on here, my screen is a little bit better here, so you can see a little bit better. But like what they're showing here is here is a gripper mechanism. There's a screw that drives back and forth here. It's driven by this nut that is actually, it's like sitting on some sort of bearings. It's rotated by this guy, which is sitting on these bearings, which is driven by this motor. So it's a little hard to see, it's a little messy, but when you start digging into it, you can start seeing where the bearing forces are, where the bearing constraints are. And so anyway, it's just fun to start to dig through these things. There's also a really cool book that I didn't bring with me because I had to return it to the library today called Robot Evolution, which is I highly recommend also. It's all about robotic mechanisms, from fingers to wrists to arms to legs. It's pretty old, but it really digs into, shows you kind of all the different constraints you're dealing with. So then I want to show you one other set of examples that I'll put this online. Let's see. Will this just take me to this link? Or is it? This one Ben found, and it's pretty awesome. It's a bunch of YouTube videos of mechanisms. And so it's just like anything you can think of. A shutter is pretty cool. You have to watch an advertisement for every single one of these things, which is a little annoying. But we'll just take a peek at one for just a second. Skip this ad in a second. Oh, but anyway, there's a lot of resources online to look at these YouTube videos. You can find YouTube videos that show you how the mechanism works. The best thing of all, though, is just find something that's similar to what you want to do and take it apart. And that's kind of the first step in any time you're designing a machine, is look at what was done before. Who else has done what mechanism or what product can you think of that's similar to what you're trying to do? I mean, you may be doing something completely new that no one's ever done, but the reality is someone did something really similar to some extent. You're just changing it somehow. So a lot of these systems have already been existing for a long period of time. I don't know what's going on. No idea what they're showing us.
Changing the speed.
Oh, is that what it is?
By how much? That's awesome. It's like sheer. Yeah.
Yeah, so that's the whole thing. So there's friction drive systems, and they're actually heavily using continuously variable transmissions now, where you have a set of spheres, and they changing on the orientation of the sphere, you change the gear ratio. It's pretty cool. So this is.
Oh, that's pretty fun.
Here, let's look it up. CBT. There you go. CVTs explain. Without pictures. Alright, so this is a crazy one. So they make them in a bunch of different fashions. This one's actually belt driven. They have this semi-rigid, semi-flexible belt. I don't think this is. There you go. So you can see there, we should stop talking about what gear ratios are. But basically, they're changing the ratio of the diameters of this as this belt is moving along, and so that changes the ratio. One spins faster than the other. So anyway, there's CVT friction drive is really crazy. tried making one of these at one point and realized that I didn't have the proper equipment to do it correctly. Maybe this shows it. Here you can see there's these spherical interfaces. I don't know, it's some sort of spherical interface. And these balls rotate, and they have a point of contact, and it moves either in to out or out to in, and that changes the gear ratio because you're getting a smaller diameter to larger diameter interface, or vice versa. And it turns out the reason you could want to do this is there's no backlash, so it's just friction. So these faces are just touching each other. Rather than if you have gear teeth, whenever you have gear teeth, you have teeth that there's some gap in between them, and when they drive one direction, they come into contact. When you reverse the direction, there's a point when they're just moving through the air, and it causes this. And so if you're trying to servo them, and so there's like a smacking that happens. If you try to servo them, like you want to control the position, there's this little slop in the drivetrain that's called backlash, and that causes huge issues in control systems. So you're always trying to get rid of your sort of backlash in your drive system. And so in robotics, like a lot of what I've had to deal with is how do we get rid of that backlash? And there's ways to do it. You can get anti-backlash gears, which maybe I should just jump into gears a little bit. I'm just jumping ahead of myself. Okay, nice. So like gears, that's probably gear will probably give us a quick little. Yeah, so there's. Let me see if there's a gear contact angle. That'll give us a good image with gear. So here you're seeing an animation that's showing. They're showing that there's actually zero gap between these teeth, but the reality is there's always some gap that you have to allow so that when you assemble the two gears together, they don't bind up on each other. They're never perfectly round, and any little bit of variation is going to cause it to bind up. And like there may be a point when it contacts too much and a point when it doesn't contact enough. But with gears, you'll end up getting a little bit of backlash in this spacing. But with continuously variable gears or friction drive systems, you're just in actual contact. The only way you transmit torque is through the metal-to-metal interface. Technically, there's a special non-Newtonian fluid in there that actually seizes up under high pressure, and it binds and actually creates the interface between the metal. So you're not doing metal on metal that actually causes galling, but it's essentially a hard surface to another hard surface. Yeah, I'm getting ahead of myself a little bit. There's other systems like harmonic gears where you preload, you stress the gear teeth into each other, and so you only contact in these two spots as you're rotating around. And you flex this internal flex spline, and that removes prevents the backlash from happening. But you also have a very inefficient drive system because you're preloading the system. You're adding a bunch of stress into it. So these things only operate at like 65% efficiency. So if you're trying to do force control on a drive system, like you've got your robot arm out here, and you want to know what it's doing whenever it's doing anything like picking up a pen and trying to write, or trying to put something into another hole. Anytime you want to know those forces, you either need to measure it at the end effector or back in the gear train. And the larger your inefficiencies, the less you actually know about what's going on at that output. So harmonic drives are nice for backlash, but not necessarily right for all your needs. So let's just go back to just kind of the overview of what I was talking about. So you want to so that was gears and stuff, right? And there's a bunch of examples that you should go back and look through, just to get a sense of what you want. But all those examples are really to help you understand what is the range of motion that you're trying to get with your mechanism. Are you trying to have just pure rotary motion, or do you want pure translational motion, or some combination of those? Do you want it moving in a spherical space? Oftentimes you can do that just by stacking rotary and linear motions on top of each other. And then and so the constraints kind of help you understand what degrees of freedom are actually going to be allowed in order to get you those motions. So when you're looking at range of motion, you've got, like I was saying, rotary and linear and linkages. And that's right, I can't draw on here, can I? Maybe get Neil's little thing. The way to get motion is basically through gear trains, like I was just talking about. or linkages. And I would argue that linkages, gear trains, cable drives, and belt drives are all the same thing, essentially. And that is, you've got like a, do I don't have a good example here. Basically, you've got, like I was showing with those gears, right? You've got a gear that's rotating, and it's interfacing with another gear. But all you're doing is you're taking that tooth and having it push along another tooth, and that rotates it around. But that's essentially just a linkage from the center of your rotation down to that tooth, and it's pushing on another one. So you can think of it as like, these are just kind of a set of linkages that are touching each other. So you can, same way you can go out, here, I can draw it, maybe I can draw it in SolidWorks.
Paint.
Yeah, paint with my mouse, I can try. Let me just show you what I'm talking about in SolidWorks.
It's not a is there a working?
I know, I need one. I was looking, I thought we would have one just laying around somewhere, but I guess not.
Did you try projecting this PowerPoint onto the whiteboard?
People complained last time I did that. We can try it. I mean, it's nice. It's like, you get a lot of glare on your side. Maybe we should. Should we try that? You just get to deal with some glare. I think that's probably the best way for me to just sketch out what we're talking about. Yeah, let's do it.
You're the boss, man, not us.
What's that?
You're the boss, not us.
Yeah. So what I mean by that is like, so you've got these linkages, right? And they're just kind of moving back and forth. Well, a belt drive is just you hook a belt onto either side of those two wheels, and as you rotate the wheel, the belt moves. And that's like, here's a little belt drive, and I just have these two. There's just a belt connecting these two pulleys, and they just rotate around each other. And what the belt's doing is basically setting a constraint, saying that the distance between this point and this point can't change, and so. And same thing on this side. And so as one of these rotates, it has to continue. That point is essentially just sliding along the tangent C and sliding along the other side, and that's what keeps your orientation. And it essentially, you want the belt to be non-extensible, just like a linkage would be. Like it's a piece of metal hanging on there. And in fact, the load member inside of the belt is actually fiberglass or Kevlar if you have fancy ones. Alright, let's see this. The other question is if you have pens. Does anyone have pens? Nobody here? I guess not. I think maybe it's not going to work at all. Alright, let's see. See if we can do this. You see that? Alright, so if you have gears, you've got these teeth all along here. And you've got them all along here. And you've got a center of rotation. And they're acting along some line. You can assume it's just a tangential line here. But usually there's some contact angle that's on the gear teeth. Usually it's 20 degrees or 14.5 degrees. But the point being is that if you're applying torque from this pulley, you're going to essentially have an arm that's applying a force that's tangential to the center of rotation. And that is going to cause a reaction force here. It's going to cause this guy to rotate around this direction. And so as you rotate, sorry, just going to go the other way. As this guy rotates, he's going to push this guy along this rotational. And so if you make them at different sizes, you can get different gear ratios. So this guy is and the gear ratio ends up just being the difference in radius between these guys, R1 and R2, or the ratio between the two of them. And so as this guy's rotating around, this guy will end up spinning a lot faster because he has to go around a whole bunch more times in order to make up the same distance around the circumference here. But similarly, you can instead of having these teeth here, you could attach a bar. And now when this guy rotates, it pulls down, it actually will rotate around and it'll actually pull this guy. Let's say he's going to go down to here now. This guy is also going to have to travel down some distance. And so you can actually end up getting rotation from this gear train. You notice it moves a different direction than the other one's going. So then you can also say, and so that's great if you want to apply a lot of torque. You can put a linkage on here that you have like a hunk of metal or something. You're actually applying those loads through a piece of metal. Similarly, but say you want it to go, say this pulley is actually like way over here. So what you can do is you can actually have, get rid of these guys a little bit, bring this up slightly. Say, okay, gears were cool, they were going to work for me. The linkage, gears were cool because it was going to give me this continuous rotation. Gears were okay for that, they continuously rotate, but the linkage doesn't work because I can't go past, the linkage can't move past this pivot point usually because you're usually supporting on two sides of your shaft. Maybe not, it depends in some situations you can, but if you want to put your, say you want a pulley over here, well, in that case, what you're probably going to do, and you're going to have some, I don't know, some joint over here, you're probably going to have something that travels along here and then comes back again. You probably have a pulley here that helps you rotate along that. And actually probably you don't want a giant guy because then they're going to be colliding with each other. There's like some pulley here. So now you can say like, okay, well I need some sort of non-extensible material that can transmit that power all the way along there. And so that may be a belt drive system, or it could be a cable drive system. So belts are rubber. That's what I have right here. There's a bunch here. They're usually rubber or polyurethane, and these are timing belts. V-belts are what you might see underneath the hood of your car. Timing belts have teeth to help take some of the torque and to make sure that it's not skipping and providing a bunch of, and keeping the timing accurate. But there is a little bit of stretch in them. But you can do full continuous rotation with them. You could also do cables. The thing with the cable is that you have the end stop somewhere. So you're probably going to need it to terminate somewhere on either end of the cable, because the cable is not a continuous mechanism. But so that gives you a wide range of motion, but not necessarily that's going to cause this guy to, so like, say this guy rotates this way, he's going to pull this way, he's going to pull this guy around like that. And so they're awesome because you can put the power where you want it. It doesn't have to be adjacent. There's zero backlash in the system, and they have a very high load capacity. But there's also pretension that's required. You need to keep your cable tight because while you're rotating this way, you've got tension along this line, but this side is becoming detension. So you're actually you can think of it as like you're pulling the material around this way and you're pushing the material this way. Cables don't really like to be pushed, right? You can picture that you're actually going to cause it. If you're not careful, you can actually cause it to pop off of this pulley that's right in here, or even off of this pulley, because you can actually end up having it bunching up all the way to the point to that last little bit of contact area there. And so you have to pre-tension the system, and you actually have to pre-tension it to about 60% of your total working load. So basically a little bit over half of what it's going to be, because that's about how much it's going to detension on the opposite side. So the problem with that is, well, so that's maybe not so bad if that's what you have to do, but you can have a problem where, because you're putting this pre-tension on, say I want to put, I don't know, 50 Newton meters of torque on the end of there, I need to, and I've got some radial distance here, I've got some tension that I need to put on there. Might be 1,000 newtons or something like that, 250 pounds. That means even before there's a load on this system, my whole system is stressed with that 1,000 newtons or whatever. And that means there's reaction forces on my shafts and all my supports. And even these little pulleys that are hanging out here still have this tension applied across them. And that's actually causing loading on my shafts. And that means I have to bulk up my shaft support system. I have to bulk up all the material that's holding everything in place. And you end up having the same situation with belt drives. So you have to have a pre-tension similar to the cable drive. But again, each of these is nice. Like this cable drive is if you need to put your power in some weird spot and you need maximum power capability, it has a very high load capacity because you can use steel cables. But you have limited range of motion. And belt drive is pretty nice. It's fully continuous, essentially zero backlash. Although there's some stretching and some non-linearity there, but it's not this like slapping back and forth with gears. It can be pretty decent. So that's just one example. What you don't see in that picture right there is that cool little hand.
I thought it was nice to note the Medela is a cable drive.
It is. It is. I'm not entirely sure why they made that choice. It might have been because they
It's
didn't.
a work envelope. They have like a lot of milling space for how big the machine is. Like in comparison, like the cable drive system is like really convoluted, but it allows them to move, have a lot of range of motion in their machine, and they can do that because it has single cell manufacturing. So they have one person who assembles the entire machine. If you had to do something like that with a kind of like assembly line situation, it would never get. It would never get too well enough for it to be able to function.
Yeah, and that's the thing with cable drives is they're kind of a real pain in the ass to assemble because you think about it, like you start having to, and then like you look at this picture over here, like oh well,
That's a full screen.
I mean full screen,
It does that.
whatever. You can just imagine that running all those cables for that hand all over the place, every one of those pulleys, you got to try to string it around. It's just, it could be a real issue, and you have to terminate every cable. Every time that cable ends and applies torque, there's a special termination you have to put on there. You have to crimp that on. That could be a real pain. So you got to be careful with those. There's a lot of overhead that comes along with them. But if you want to put the power, like it's used a lot in robotic hands because you put all the gearboxes down at the base, and then you just run lightweight cables all the way up to the ends. So constraints is a big one to keep track of. Neil likes to talk about the Maxwell stability criteria. Basically, all that's saying is that anytime you've got a node, it has these six the X, Y, Z. You know, you've got your translation and your rotational. I got my directions wrong. Whatever. You basically have 6 degrees of freedom that you need to constrain. And this equation is basically saying you look at the number of struts, so you've got this box, and you want to constrain it. You look at how many constraints you have, and that tells you how many nodes and how many struts, and that tells you what kind of constraint you have. So here we're in 2D, so we've got X and Y, and rotation around X, Z. We've got X constrained. We have Y constrained, but we don't really have X constrained, so this box can actually move back and forth. In fact, that turns into something called a 4-bar linkage, where you look at these pins are able to rotate about these 2 points, and so you can see that this box could easily step over here and just rotate around. But we have a constraint around our Z-axis right now, so it's not actually able to rotate. So it actually stays flat. It just moves in this linear motion and a little bit up and Y. So it's something to keep track of whenever you're trying to design something. You kind of got to get in there and dig around and figure out what that is. What that kind of helps you think about is, say you want a rotating shaft. You want to support it by a bearing. It also kind of helps you with so if you're trying to make something, you're trying to, say you have a cart. You can think of this as like on the machines you're building right now from James and Nadia's work. So there's this rail running along it that's fixed on either end, and you've got this shuttle that moves back and forth on it. Well, the shuttle has guideways on it. It's moving along these 2 rods, and there's these 4 pivots, and there's a drive system along the center of it, and that's what's actually causing it to drive. Now, if you didn't have all these supports on it, what might end up happening, and say you were, I don't know, say it was in a different configuration. So they made it really nice and balanced, so it operates pretty smoothly. But what if you only had just one? You're like, okay, I'm just going to put this one bearing on it, and I'm going to put this shaft through here, and I'm going to apply a load in this direction. Well, if you only have one bearing here, you really only have one constraint that's keeping you. And so as you try to drive it, this thing's going to try to rotate and start to bind up on you. And so you end up wanting to start realizing, well, I want to put another bearing in there to prevent it from kind of flopping around. And that essentially gives you these two constraints here that allow you to translate still. So you say, okay, I've got this guy constrained. That's cool, but they're pretty close together. If they're really close together, then essentially, like if this guy moves over here, it essentially becomes the same as if it were just, it keeps moving over, it ends up becoming the same as just this one. And it's actually not stiff and doesn't prevent that rotation. So in your design, you want to push out that support as far as your packaging will allow you to do that. And that provides a larger moment that these guys can resist. So basically, the further out they go, it's just like holding on to, I don't know, say you're sweeping something out of the pool, you got like a big old, net, and you're sweeping something out of the pool, you're going after butterflies or whatever. If you only hold on to it with one hand, or if you hold your hands close together, I guess with a baseball bat or something too, you hold your hands really close together, you don't necessarily have the ability to apply a lot of torque. The further out you move your hands, the more torque you can apply. And that's the same thing here. It's like this becomes your pivot point, and this is your reaction force here, and you're able to apply a larger torque, which counteracts this applied force here, which is your shuttle, which is driving you. And so you can sit down and start to actually calculate out all of these things, calculate your forces, and figure out what is the distance that this guy needs to be. And I'll do that like if I'm trying to build a rotary joint for a robot or something like that, I will start to calculate out the spacing between my bearings so that I can actually get the stiffness that is required. So I might say, I need to reach this far out with this length of a beam. I'm going to have this much torque on it. I have some stiffness of that beam. I need to be sure that those joints are going to withstand the load, so I'll size my bearings and the constraint system around that in order to balance out those forces. And of course, I want some headroom on top of that. So that's just got like a really quick way of looking at this idea of constraints. You kind of want to sit down there and draw out a free body diagram of what you're working on, so you kind of have a sense of how accurate it needs to be. Power transmission. This is actually power prime movers. Is probably a better description of this guy. So what you're playing with right now are stepper motors. You may have played with servos so far this semester. But there's a bunch of different types of motors that are available. There's DC motors, there's brushless DC motors, there's AC motors, and then the steppers and solenoids. And of course you can get into hydraulics, which has its own huge issue. Are you guys familiar with the differences between all these different types of motors? Some of you are, some of you aren't. A stepper motor is really good for position. So if you want it to just go to a position, the beauty of it is because it's just making incremental steps, you can actually run it open loop. You don't have to keep track of where it's going along that. Each step of the way is just stepping along, and that's easy and fine to deal with. But it can't really do velocity profiles very well, and it can't hold a position very well. You can't just dump current into these things. So what you can go, so most robotic systems and like most like high-end CNC machines run either DC or AC motors. And actually the AC motor starts to become essentially the same thing as a brushless DC motor. I don't know if I want to draw it out. A DC motor, the main point of a DC motor is, so you've got your motor shaft, you got your magnet thing going around it, and you got your coil. I always forget the coil's on the inside or outside on these guys. I guess it's probably on the outside. But you got your magnets in there, you got your coil in there, and usually there's a set of something called brushes, and there's actually these. You get commutation from having brushes that are attaching to contacts that are sending power to the coils that are inside the motor that are generating the torque. And so it's literally a mechanical system. There's these carbon brushes that have power going into it. It's called positive and negative. And it's literally just these contacts that start and stop again. And that changes the direction of the magnetic field in here so that it can continuously rotate around one direction. And they're great because they're cheap because this is just carbon and some metal and copper and stuff like that. And you can dump as much current as is necessary as you can keep this thing cool in order to generate torque. But these brushes, every time that brush passes over this little gap, it sparks a little bit. And that gives high frequency noise, which ends up generating a whole bunch of noise in your system. So if you have a lot of digital electronics near your motor, you're probably going to end up getting a bunch of noise popping off from it. And right now, if any of you are building any systems with DC motors for your final projects, I highly recommend trying to get all the stuff that you're going to be using running. It doesn't have to be all finished and packaged, just put it next to itself and run it and see if you get noise, because you're probably going to have to deal with that. And that's usually some sort of grounding issue or shielding issue or something like that you can deal with. So that's a DC motor. Brushless DC motor is kind of the same thing, except instead of mechanical connections, it's induction. And so you actually just induce the magnetic field in the copper wires that are running over here. And so that means without the physical contact, you don't have any wear property. Like there's nothing that's wearing away. You eventually have to replace brushes in DC motors. The brushless DC, you don't have that problem, and so they're much more efficient. They're usually a lot quieter. They're quieter electromagnetically as well. But you have to electrically control the phasing or the commutation, which is the changing magnetic field that's inside the motor that's actually generating the torque. But you can buy off-the-shelf little controllers that do that for you. It just costs a little bit more. And then AC motors are essentially the same as a brushless DC motor. It's just that the AC waveform, there's synchronous AC, and then just an AC motor. An AC motor just plugs into the wall, and this is like what your fan is. Your fan has, like, if you just have a wall fan or a box fan or something like that, it just takes the AC waveform that's coming through the wall, the 60 hertz, and uses that for commutation and spins the motor at some standard speed, and so that's just controlled speed. The only way to change that is to have a variable transformer. Synchronous AC is basically the exact same thing as brushless DC, only has this nice smooth curve, whereas with the DC motor, you're actually generating your PWMing to generate the signal. But in all these cases, all these non-stepper motor configurations, you need feedback in order to get to some sort of position. So like the stepper is beautiful because you have this you can just run an open loop, you just count the steps and that's where you're at, hopefully, as long as you didn't run into anything. But if you want real precision, you need to close the feedback loop so you really know where you are. So in that kind of situation, you're going to have you got your motor, and it's driving whatever. You've got your drive system, and then at some point you're going to, maybe at the motor, you might do this, you're going to have a thing called an encoder attached to it. And the encoder usually has like 5 wires coming off of it. And it's literally just counting the rotations for you, counting the angular position for you. And you take that and you bring that back into your controller, and that's going to tell you, and that you're going to use that to keep track of your angle and direction. And that'll help you close the loop and actually drive the system. So anytime you need like high precision or real power generation, go with the DC or brushless DC motor. A manufacturer that's super high end that all robots have are Maxon motors, and they're like $600 a motor, but you get what you pay for. And now there's a big interest in hobby motors, outrunner motors, which you've probably seen on all the quad rotors that people have nowadays. Those are brushless DC motors, but you need to put and you actually can drive them, but they just generally have a really low inductance, so it's just a different type of motor than is normally driven. So off-the-shelf options for driving them in a servo position controls that quite exist. Let's see, more power. I was just saying, gearing. This is a differential for the wrist of a robot. We use a similar thing in some of the robots I had done. It's pretty commonly used. It's cool. You can start to get into all kinds of fun things with gearing mechanisms where you can, like in a differential, this is the same thing that happens inside your car. You have 2 gears, and if you rotate them together, like these guys here, you rotate them together, it locks up that gear on the output, and that gear just pitches forward and backwards. If you rotate them in opposite directions, it causes that gear to rotate, and so you get twist and pitch all from these two all from this one centered gearbox system, and that's really nice when you have your axes actually aligned in the center, in the same point, because that's similar to what we do with our wrist. Rather than having a bunch of stacked joints that start stacking up and then your wrist gets really big and long. Like I said, I think I already said the gearing is already kind of a main thing. So let me hit just this. This is basically the most. There's like two of the most important things. The two most important things when you're doing mechanical design are thinking about your constraints, how you're lining everything up, and keeping track of stiffness. And I think that stiffness really doesn't show up well there, huh? Stiffness is this thing that is. Stiffness is really what you're looking for in your design most of the time. You're not usually limited by strength, you're usually limited by stiffness. That is, it's not how strong of a mechanism you're building, it's how floppy is the mechanism that you're building. There's always going to be some elasticity to any material, and there's always going to be some flex to it. And you're really fighting the flex more than you are the strength in most situations. At least that's been my experience. And something to keep track of is say you've got this beam, and it's fixed on one end, and you're applying some load over here. It's going to have some sort of deflection. And this deflection is proportional to your applied moment, or basically, this force times some distance here, or it could be just an applied moment. Divided by EI. And there's a bunch of other conditions there. That's basically what that equation is showing you. Let's get rid of some of this. So what is E and I? E is material dependent, and I is geometry dependent. I have one of these. So what does that mean? So what it means is there's only so much you can do with your material properties, right? There's only so many materials that are available for you to work with. And there's a lot of materials, but there's only so many, right? And so E is a material property. E is your elastic modulus. And this is defined as if you apply a load, a stress to your material, you look at how much it strains, and you end up getting a curve that looks something like that. Maybe it breaks right there or something like that. And there's this linear zone, which is defined as, which is the elastic region of your material, and that's defined as how much load can you apply, and when you release that load, you come back to within, I think it's 0.02% of your original dimensions. And so there's a certain amount of stress that you can apply, and there's a certain amount of elongation that happens during that stretching, that elastic motion. And the ratio of those is E, your elastic modulus. Yeah?
So that line is like perfectly straight up to where it starts to bend just a tiny bit, and you stop saying that it's perfectly straight when it's outside of that 0.02%?
Yeah, so I mean it's perfectly-ish straight.
Right.
But yeah, you essentially assume there's a region in there where when you return back, you're within this 0.02%. Once you go beyond that, you start entering, so this is your yield limit. So there's sigma y is your yield limit. And then there's a ultimate stress limit, which is usually considered somewhere up here, where you start entering into plastic deformation. And that's like an easy way to describe this is like you take a plastic bag, like polypropylene bag that you got at the grocery store, and you can pull on a little bit and it kind of returns. But if you pull on it slowly, it stretches and stretches and stretches and stretches. It's still holding some force, but you've entered into this plastic. When you're just pulling on a little bit, you're in this linear zone. As soon as it starts stretching out, and it's not going to return to its shape, you've entered this zone, and this is the plastic deformation zone. And then eventually, it breaks somewhere out here. All this time, you're absorbing energy, which is something to keep track of if you're interested in absorbing energy. This is, you are absorbing energy, you're putting energy into the system at some point here, but it's not necessarily useful for traditional machines where you want everything to retain the shape that you originally want it to be. And every material is going to have different properties, but usually around this, they have some zone around here, or at least engineering materials have some zone around here. Wood has it, plastic has it, ceramics have it. You know, a brittle material. So there's different materials. There's like, if it's really brittle, say it's a ceramic or glass, it might look like this, and then like just break right off. If it's something that's very ductile, it may look something like this, or it may look even something more like this. And so what you want to look at is what is the slope of that line, and is that something that's useful for you or not? There's all this discussion of like aluminum bicycles versus steel bicycles. I recommend you go and look at the elastic modules of those two materials and think about it a little bit, because what it is they're playing with, that's a discussion about this, but people aren't talking about this part, which is also part of the stiffness equation. And this is geometry dependent. What that is that this is, I is the second area moment of inertia. Second area moment of inertia. And it's basically telling you it's purely a geometry term. There's an equation for it that I'm not going to write out because I don't have it memorized. But every geometry, whether it's a box or a really thin, long piece, or if it's a rod, or if it's a tube, or if it's some crazy complex geometry, every one of these has a second area moment of inertia. And depending on how you load it, you're going to get, you're going to have a different amount of stiffness. And you can imagine, you can just picture probably at some point in time you've bent, you know, say, I mean, even like a piece of paper, right? Like a piece of paper is super thin, right? Super low aspect ratio, and it's super bendy, right? But as soon as you stack a whole bunch of them up together, they actually start to become a lot stiffer. Now, that's of course not allowing them to slide back and forth between each other. And then you can say like, well, and then you can say, what exactly is going on here? Well, when you have, that picture up there is showing you, when you have a bending beam, there's tension, so you bend it. There's tension on one side and there's compression on the other side. And there's some point in the middle here. It's called the neutral axis, where there's actually no load on your beam. And if you're very narrow, you have a very narrow profile, your tension compression is very close to that neutral axis. And so you actually don't have a lot. The way I always think of it is it's essentially the same thing as the stiffness of your bearing stack. It's the further away I put my hands to support something, the more torque, or the less amount of force I actually have to apply to make that system stiffer. And so it's the same thing as like you put your mass further away from that neutral axis, the more strength it has to actually, for the same amount of force, the more effective it is at actually resisting that tension. And there's equations to describe all that stuff, but you can just think about it. Like that's why we make things like I-beams. Right? So the I-beam has all this mass up here and all this mass up here, because this is where all your tension is going, is along these lines. Like if you extrude this out, let's say we're going that direction. That way. If you extrude it out, so these are always used in bending in this direction, and so you have all this, you got all this mass up here that can take tension, and all this mass down here that can take compression, or vice versa. And so you can really affect your geometry to become a lot stiffer for a given amount of weight by just putting the geometry where you need it. And that's why for the weight, a hollow tube is much better than a solid round bar. And essentially what you're saying is, what's happening, like we were saying, is all the tension is the majority of the tension is far away from that neutral axis. It doesn't really do, the material that's near the neutral axis isn't doing you any good. So just putting more doesn't help. You need to put it far away. And that's why composites, like high performance airplanes or cars or something, have the foam core with carbon fiber. Right? So you've got carbon fiber, you've got this foam core, in between them. The whole point of that is to put the carbon fiber, put the fibers that are taking a load. The fiber is the thing that actually takes the load, right? And so you put them as far apart from each other as possible, so that they can actually resist that stress as much as possible. And so the combination of geometry and material combines to reduce your overall deflection. The higher you can make those numbers, the lower your deflection ends up becoming. And I think this is something that people forget about all the time. That you have the most control over your geometry. So use your geometry to your advantage to make the structure as stiff as possible. And that just takes us to the last point I had, which was your fabrication process. Your material selection and your geometry define the stiffness, and all that's based on how you're actually going to make the thing. If you're going to make it out of sheet metal, or if you're going to machine it, or you're going to 3D print it. You can actually get somewhat strong 3D printed structures because you have a lot of you get complexity for free, so you can actually put the geometry where you want it, but you're highly limited by that overall material capability.
What do you mean by that? The complexity where you want it?
Well, that's the one nice, the nice part about 3D printing. And there's some nice things. I'd say the two nice things in my mind about 3D printing are, one, I don't have to stand at the machine while it's operating. That's awesome. And two, you get complexity for free. It takes just as long to make a long bar as it does to make a long, tall, fat bar the same height. It takes pretty much as long as if I had a bunch of weird, complex stuff and weird scaffolding inside of it. You don't have to worry about the manufacturing process because you can just go layer by layer by layer. Whereas if you're machining something, you need to keep track of how you're getting in there. Like, say I wanted to machine this I-beam. Well, I need to get in, say I start with a square, I need to be able to get in here and machine out that whole groove. And then I need to get to the other side and machine out that groove. So am I going to take this part and flip it and then machine it twice? Or am I going to get some super fancy machining center where I can rotate it and machine it twice, like a 4-axis machine or something like that? Or am I going to make it out of 2 different pieces or 3 different pieces, and I'm actually going to put a bunch of holes along here and I'm going to screw them together? Something like that. Who knows? All those things are going to play into the overall stiffness of your system and the overall capabilities of your system. So like for instance, when I was building the last robot arm I was building before coming out here, we were looking at how we were going to make this thing. Originally, we did everything as milled aluminum, just these huge hunks of milled aluminum, which was really cool looking, but really, really expensive because I had to spend all that time machining away all of that material in order to get nice thin walls. There's a limit to how thin of a wall you can get when you're machining in general. So we ended up looking at a bunch of different manufacturing processes. And we wanted to do it potentially at volume also. So we were looking at casting, we were looking at sheet metal, we're looking at composites, all these different things, and they all have their trade-offs. You kind of have to go through that whole iteration cycle of, okay, depending on manufacturing process, I'm going to have certain materials available to me and certain geometries that are available to me. And I have to play with both of those things in order to get to some reasonable amount of deflection here. Then you have to choose a deflection that you can actually hit. And there's just certain limits based on what your overall, what all the options are here that are possible. Then of course you throw in your different drivetrains and you just start iterating amongst all those things. So that's a really quick kind of rough thing on machine design. I can show you some mechanism design stuff if you're interested. I'll just show you some quick little things you can do in SolidWorks. But if you have any specific questions, I'm happy to answer. Yeah?
What's the difference between mechanism design and machine design?
Mechanisms are used in machines, I would say. Machine design is what we were just going over. So there's like machine component design books. And then there's like system integration. That system integration is when you throw electronics onto the mix. Yeah.
So you talked about the slider mechanism with the 2 parallel linear slides and 4 bearings that are on them.
Mm-hmm.
That's actually over-constrained, right?
It is.
So how are strategies to that?
So you actually usually will build some sort of compliance into the extra constraints. So like on the MTM machines, the way they dealt with it, and Nani could probably talk about it better, but they actually allow, they actually put some flexure into the structure that's supporting the shaft. And I think they heat it and kind of move it back and forth in position to align them to get them centered. Like on a precision machine that's doing like high accuracy silicon wafer stuff, they just machine it perfect. They just make it perfect, and you pay for it. That's why it costs $100,000 per axis, something like that. But other ways to do it are you add compliance. Like on this little thing, it's still real junky, but I put rubber sleeves on one side of the shaft so the shaft can move around, so that I'm not binding it up as it's going around. So I've got like my constraint along this axis, and then this guy's providing constraint on this axis. But I'm allowing, what I really should do is actually control which degrees of freedom I'm actually trying to prevent from being over constrained. But I got lazy and I just put a piece of rubber in there, so I'm just gonna whip it all around. And I said that was okay for my purposes. But you do want to look at like where your constraints actually are. So that's like one quick, easy thing for you guys to. Alright, I got it. So like, okay, so you're making two pieces clamshell that fits together. So you've got an A side and a B side, and you want locating features. The most common way to do it is you put a pin, and you put two pins down, and on the mating piece, you put a hole, and you put a slot. And the slot is there so that this guy constrains you in X and Y, and then when you slide this guy down, so you got this pin here. It's essentially, you say this fit is pretty nice, so it sets you in X and Y. But if you were to put another hole here, then you're over constraining it in X. But the whole point of that guy is like you've already got X and Y locked down here, so it doesn't move. All you're trying to do is prevent rotation around Z with this pin. So you don't want to be super tight all the way around the shaft. You want to allow some room for some tolerance and some variation. And so you can put that pin over here somewhere, and you just want to make sure that you line up that slot to match the constraints that you're actually trying to withstand. So it's like you kind of need to draw out where your variation may be, and then allow some compliance in there. Either just a hole, or if you build something, some flexure or something like that. Reach all these guys. I was going to show you guys something that I've recently learned about in SOLIDWORKS. You can do physical dynamics, which are kind of cool. And it's reasonably okay. So I used it to model one of those red guys there. I'll show you that. Let's see if it works. I was trying to save a video of it and it kept crashing my computer earlier, so we'll see if we can actually. Let's see.
Matt,
Yes.
maybe not tonight, but at some point, do you have like a tutorial on like your naming?
My naming convention?
Yeah, because you had mentioned it earlier, and it's a good one.
I have a document somewhere.
Do you?
Somewhere.
Just dig it up and share it.
Oh, that's not working at all. That's funny. What's the other computer? I have to recalculate it. Let's try the other one. Oh. Huh. I think it's working now. Let's see if it did it. So, let's see, I think I can slow it down. So it's actually tracking the interaction between the gear teeth, which is cool. So what I was trying to simulate was, so what I was working on, so I've got this mechanism that I want to use for my walking robot. And I'll show you maybe I should show you that video so you have an idea what I'm trying to get at. But so this guy's nice because I get timing with the belts. But I wanted to change the motion profile. So I made this thing so that I could try to make the motion profile go where I want it to go. So I could just like track a line. So it's essentially a cam follower system. But I want my feet oriented in a certain way. And so I want to keep that timing between the output and the input. And so I was playing with this guy, and then I made this guy. And I made this guy, I was like, man, I know this thing works. But when I made this, it kept not working a little bit. And it was just because I was getting slipping, because I made it out of acrylic and little O-rings. So then I actually went ahead and made the full assembly and the full simulation and proved that it does work. But you see there's all these complications, right? Like this gear train, these shafts need to be supported on multiple sides. I'm even supporting some of them on one side, some on the other side. And I start getting, there's depth that all these mechanisms take up. It's just things that need to be kept track of. But then so that's called physical dynamics, and that's in the basic motion package. You all should have access to that. There's also this other cool one you can do. Hopefully this one works. I don't know if it will. So this one I was just playing with having track followers. Does this work? Yeah, so what's fun is that it actually keeps track of the track that is moving along, and it's actually doing some actual physical dynamics that try to prevent collisions and try to prevent actually like passing through a material. And so you can really start to work out different motion paths with your mechanism. And I designed, like I had talked about before, if you guys came from my other SolidWorks talk, I do everything as master model initially, and then lay it out, and then I'll build an assembly if I want to do these kinds of analyses. So I probably did, if I open this part, yeah. Oops. Edit context. So I drew out my interface. So again, like everything is drawn out just as this one sketch, and then and I even have the little gap in there, so you actually need a little tolerance so that the thing will actually fit. Draw in all of those little details, and then you can just blast through making a bunch of actual bodies, and then you can export them all as saved bodies, and then you can generate your assembly, where you can actually do your simulations. And someone had mentioned in the last class about doing the physical dynamics stuff, and he was talking about something I didn't even know was possible, which is super cool. No, this one's, the constraints are all messed up. But if you use a tool that I never ever use, which is, you click on this little guy, instead of free drag, you can do physical dynamics on it. And you can actually do checks between parts. It's not going to work for me right now because my constraints are all confusing, but it's just, you can play around a little bit with checking it. It basically will stop at collisions for you. So if you're trying to figure out the range of motion of a mechanism, use that move tool instead of just free dragging things around, which is what I always do. So I didn't even know that was possible. Let's see. What else? So that's pretty much all I had specifically to show you. You guys have more questions? Or anything you're working on right now that's giving you trouble? I mean, the main takeaway from my point of view is stiffness is geometry and material dependent. That's the #1 thing that people mess up and have a misunderstanding of. And then the other thing is keeping track of your constraints so that you understand what has to move in, that you're not over-constraining something so that it doesn't fit well together. Yeah.
Could you just go over what all those different things mean? Because it's hard for me to imagine how you'd count mechanisms, for example.